What could destroy the most powerful rocket ever built? Not the engines, not the fuel, not the flight computer. It might be the tiny heat shield tiles covering its skin. That sounds impossible. Starship V3 is built to punch through the atmosphere, reach space, and come back again. But the most dangerous moment is not liftoff. It is the return. As the ship falls back toward Earth, everything changes. It is no longer climbing away from gravity. It is slamming into the atmosphere at brutal speed. The air in front of it gets crushed. That crushed air turns into extreme heat. And suddenly the sky becomes a wall hot enough to punish every weak point. Now look at the outside of the vehicle. Those small dark tiles do not look powerful. They do not roar like engines. They do not glow like fuel. They just sit there on the surface. But during re-entry, they become the first line of survival. If one tile shifts, a gap can open. If one gap opens, heat can slip inside. If heat slips inside, the structure underneath gets exposed. And once that begins, the problem can spread fast. From the outside, everything may still look controlled. But beneath the surface, the real test has started. That is the strange paradox of Starship V3. The biggest rocket on Earth may not fear its biggest parts. It may fear the smallest weakness in its outer skin. So the real question is not just whether Starship can fly. The real question is whether it can survive coming home. Because if these tiny tiles fail at the wrong moment, the entire dream of reusable spaceflight gets tested in seconds. So what actually happens to Starship during re-entry? And why can a small piece of heat shield become so dangerous? To understand that, start with the return path. Starship V3 is not gently falling home. It is moving through the upper atmosphere at extreme speed. At that moment, air becomes the enemy, not because it is sharp, not because it is solid, but because it gets compressed violently ahead of the ship. That compressed air becomes brutally hot. It builds around the vehicle like an invisible furnace. From the outside, it looks like re-entry. From the ship's point of view, it is a collision with the atmosphere itself. Now picture the vehicle rolling into this heat. One side faces the worst of it. That side needs protection everywhere. Not just near the nose, not just near the flaps. Everywhere the airflow can bite into the surface. This is where the heat shield tiles come in. They are not there to help Starship climb. They do not create thrust. They do not steer the rocket. They do not make the engines more powerful. Their job is much quieter. They sit on the outside and take the punishment first. They are the skin that gets burned so the body survives. But that skin has a terrifying weakness. It is not one perfect solid shell. It is made from many separate pieces. Each piece has edges. Each edge has a gap. Each gap has to behave perfectly under stress. And that is where things get dangerous. Because re-entry is not just heat. It is heat plus pressure, heat plus vibration, heat plus twisting forces, heat plus the memory of launch. Every tile has already been shaken during liftoff. Every tile has already felt the vehicle flex. Then, on the way back, it gets hit again, this time by the atmosphere. So what happens if one tile is slightly off? At first, maybe nothing dramatic. There may be no instant failure, no huge flash, no obvious warning. But behind that tile, conditions change. Heat begins exploring the weakness. It looks for the easiest path inside. A tiny edge becomes important. A small seam becomes a question. Is the bond still holding? Is the gap still protected? Is the surface still smooth enough? Because at re-entry speeds, smoothness matters. Air does not politely flow around mistakes. It grabs them, it pushes them, turns small imperfections into hotspots. That is the domino effect. One tile moves. A gap appears. Heat enters the gap. The material underneath starts warming. The structure below feels stress. A sensor may notice something strange. The flight computer may start adjusting. The vehicle may still be flying normally. But now, underneath the surface, the problem is active. It is no longer just a missing tile. It is a hidden pathway, and that pathway leads straight into the machine. This is what makes the heat shield so strange. It looks passive, but it controls survival. The engines get all the attention. The fuel tanks look massive. The flight computer sounds advanced. But during re-entry, those tiny tiles become the front line. They work, the ship gets a chance. If they fail, everything behind them gets tested. And that test happens fast. There is no repair crew outside. There is no pause button. There is only the vehicle, the atmosphere, and seconds of extreme heating. But the danger is not just destruction. That is the obvious fear. The deeper problem is reuse. Starship V3 is not trying to be a one-time machine. It is trying to come back again and again. That changes everything. Surviving one re-entry is hard enough. Surviving it cleanly is much harder. Because after landing, engineers must inspect the ship. They need to know what survived. They need to know what weakened. They need to know which tiles stayed perfect. They need to know which ones almost failed. A vehicle can come home safely and still be difficult to reuse. That is where the real pressure begins. Imagine Starship returns with heavy tile damage. It may have survived the flight, but can it fly again quickly? Can it be checked fast? Can the weak spots be found reliably? Can the heat shield be trusted next time? If each return creates a long repair process, reuse slows down. If reuse slows down, the whole idea changes. The dream is not just landing a rocket. The dream is making spaceflight repeatable. And that means the heat shield is not a side detail. It is part of the business model of the vehicle. It decides how fast the ship can return to service. It decides how much inspection is needed. It decides how much confidence engineers can have. A single damaged region may not end the mission, but it can reveal a deeper question. How much damage is acceptable? How much is too much? And how do you know the difference before the next flight? This is why the smallest parts become so important. Every tile is part of a larger promise. The promise that Starship can survive the sky, return through fire, and then do it again. But each reentry writes a report onto the vehicle's skin. Burn marks become evidence, gaps become clues, loose areas become warnings. The heat shield becomes a crime scene for physics, and engineers have to read it perfectly. Oh, the mystery keeps tightening. The strongest rocket is not only fighting gravity, it is fighting the atmosphere on the way home. It is fighting heat through thousands of small surfaces. It is fighting uncertainty after every flight. And the question becomes much bigger now. Is this really just about protecting Starship once? Or is the heat shield the key to proving Starship can become truly reusable? This is where the story flips. The heat shield is not just protection, it is the whole test. Starship V3 is not trying to be ordinary. It is not trying to fly once. It is trying to come back clean enough to fly again. That single word changes everything. Again, a normal rocket can finish after one mission. It can burn, break, separate, and be replaced. But Starship is chasing a much harder idea. Launch the vehicle, bring it back, inspect it, fix very little, then send it up again. That sounds simple. It is anything but simple. Because now, survival is not enough. A ship can survive reentry and still fail the bigger goal. If hundreds of tiles need replacement, that matters. If hidden damage takes weeks to find, that matters. If engineers cannot trust the surface, that matters. The vehicle may have landed in one piece, but the reusable system is still wounded. That is the hidden pressure behind every tile. Each one is not just shielding metal. Each one is protecting the future flight schedule. Now think about what happens after landing. The rocket is quiet. The flames are gone. The cameras stop shaking. But the real investigation begins. Engineers look across the skin. They study dark patches. They inspect worn edges. They search for tiny signs of heat. Every mark tells a story. Every missing piece becomes evidence. Every strange pattern becomes a clue. It is almost like reading a crime scene. Except the suspect is the atmosphere, and the victim could be reusability itself. This is why the tiles become data. They are not just armor, they are witnesses. Each tile records part of the flight. It shows where heating was worse. It shows where airflow behaved differently. It shows where the vehicle flexed under stress. It shows where the design may need changes. So after every re-entry, Starship carries home a report. Not on paper, not on a screen, on its own burned skin. And that report has to be read perfectly, because the danger is not always obvious. Some damage is easy to see. A missing tile is hard to ignore. But what about a weakened bond? What about a tiny lifted edge? What about heat reaching behind the surface? What about damage that looks harmless today, but worsens next flight? That is the nightmare of reusable spaceflight. The question is not just, did it survive? The question is, can you trust it again? This turns Starship into something very different. It is not just a rocket. It is a machine trying to become infrastructure. A rocket launch is usually an event. Rare, expensive, dramatic, and carefully staged. But Starship V3 is chasing something more radical. It wants spaceflight to become repeatable. Less like a one-time spectacle. More like a system. More like a vehicle returning to service. That dream depends on inspection speed. It depends on confidence. It depends on knowing which scars matter. And that is the second paradox. The more often you want to fly, the smaller details become. Not less important. More important. Engines are still critical. Fuel systems are still critical. Guidance is still critical. But fast reuse lives in the margins. A seam between tiles, a hotspot near an edge, a repair that takes too long, a sensor reading that seems slightly off. Those tiny details can decide everything. They decide whether Starship flies again soon, or waits while teams chase hidden damage. This is the part people often miss. The exciting moment is the launch. The dramatic moment is the landing. But the revolutionary moment may happen afterward, inside the inspection process, in the quiet hours after the flight, when engineers ask a brutal question. Is this vehicle healthy enough to go again? If the answer is yes, the dream moves forward. If the answer is uncertain, everything slows down. And uncertainty is expensive. So the heat shield is not just a wall. It is a filter between dream and reality. On one side is the promise, huge payloads, repeated flights, a new way to reach orbit. On the other side is physics, heat, vibration, pressure, and time. The tiles sit right between them. If they perform well, Starship gets closer. If they demand too much repair, the system becomes harder. The rocket may be powerful, but power alone does not create routine spaceflight. This is why the smallest pieces become so strange. They look like simple blocks on the outside, but they hold a much larger question. Can a giant spacecraft survive re-entry repeatedly? Can it return with predictable damage? Can teams inspect it fast enough? Can repairs become routine? Can every flight teach the next flight? That is the real test hidden behind the surface. Not just one beautiful return, a pattern of returns. And now the original mystery looks different. The issue was never just a few tiles. The tiles are the visible edge of something deeper. They reveal whether Starship can handle Earth twice. First during launch, then during return. Going up tests thrust, coming down tests patience. It tests heat protection, it tests data, it tests inspection, it tests the entire idea of reuse. That is why the heat shield matters so much. It is the skin of the vehicle. It is the memory of the flight. It is the warning system after landing, and it may decide how quickly Starship flies again. The biggest rocket on Earth does not only need power, it needs a surface that can survive punishment. It needs damage that can be understood. It needs a return clean enough to repeat. But what is Starship V3 really proving? Not just that it can reach space, not just that it can come home. It is trying to prove something far harder, that a spacecraft can face the atmosphere again and again, then return as a machine, not a museum piece. And if that works, the heat shield stops being a detail. It becomes one of the keys to reusable spaceflight. But if it does not work, the problem grows larger. Because then the weakness is not one tile. It is the entire rhythm of flying again. So, what is the answer? How can the strongest rocket fear tiny tiles? Because spaceflight is not just about power. It is about controlling every weak point. Every launch tests the engines. Every return tests the skin. Every inspection tests the entire promise of reuse. Starship V3 may look like one giant machine, but it is really a chain of thousands of details. If one detail fails, the chain gets questioned. Not always in a dramatic instant. Sometimes it happens quietly. A tile shifts, a seam warms, a sensor sees something strange. A repair takes longer than expected, and suddenly the question changes. Not did Starship survive, but can it safely fly again? That is the difference between landing and reusing. Landing is a moment, reusing is a system. It needs heat shield confidence. It needs sensor confidence. It needs repair confidence. It needs teams to understand the damage fast. Because if every flight creates a mystery, the rhythm breaks. And reusable spaceflight depends on rhythm. Launch, return, inspect, repair, repeat. That is the real machine, not just the rocket itself. This is why those tiles matter so much. They are not just small blocks on steel. They are the gatekeepers of the next mission. If they protect the vehicle cleanly, Starship moves closer. They come back damaged unpredictably, the challenge grows. The dream does not disappear, but it becomes harder, slower, and more expensive. That is the strange truth here. The future of massive space transport may depend on boring details. Edges, gaps, heat marks, inspection time. The quiet things after the cameras stop watching. So the next time Starship V3 rises into the sky, watch the launch, watch the fire, watch the engines shake the ground. But remember this, the real test may begin on the way back, when the atmosphere hits the surface, when heat searches for weakness, when tiny tiles decide what survives. And if Starship is ever going to fly again and again, the most important moment may not be liftoff. It may be the cleanest return, because the revolution is not one spectacular flight. It is proving the machine can come home, be trusted, and do it again.